Welcome to the presentation of our work titled Model-Agnostic Counterfactual Explanations of Recommendations. Consider a user that wants to buy some clothes. As he's browsing this web store, she's receiving recommendations from the system. One of these recommended items, a pair of slippers, seems quite strange to her. She thus would like to know why she received this suggestion. She's looking for a recommendation explanation. The recommender system tries its best to provide with an explanation. There have been several proposals in the literature for generating explanations. Very roughly, they can be organized into three classes. First is the class where the recommendation model is considered interpretable either by nature, it is a simple model, or by design, a complex model adapted with interpretability constraints. In that case, generating recommendations is considered an easy task. However, in many cases, the model is not interpretable by nature or cannot be adapted. In these cases, one can only provide post hoc explanations by observing the model's behavior after it is trained. An important distinction is on whether access to the inner workings of the model is available. If yes, we are talking about a gray box model where we can identify associations between inputs and outputs. For example, we can deduce the influence of its training data points. Explanations such as these have high fidelity, meaning that they can accurately interpret the behavior of the model. If access to the inner workings of the model is not possible, we are talking about a black box model. In this hard setting, the standard approach is to train a simple and thus interpretable surrogate model locally on the neighborhood of the recommendation to be explained. Explanations are then generated from this surrogate model. Such methods have the advantage that they work irrespective of the recommendation model, but suffer in their fidelity and in that they require ample data in order to train the surrogate model. Our focus is on this black box situation, but we take a different approach than literature. We are looking to provide counterfactual explanations for black box recommenders. Let us revisit our example. The user has some interaction history based on which the recommender system compiles a ranked recommendation list. The user wishes to find out why a particular item, the explanandum in blue, is recommended to her. The explanation engine then identifies which of the user's interacted items, those in orange, are mostly responsible for producing that recommendation. The explanation thus reads, had you not interacted with the orange item, you would not be recommended the blue item. Such an explanation mechanism has the advantage that it is model agnostic, has high fidelity as it is not based on a surrogate approximation, and requires a few data, such as the user's interaction history. When looking for counterfactual explanations, we need to define what constitutes a good explanation. There are two aspects. First, an explanation should be short, consisting of a small number of interacted items. Second, an explanation should be potent in that it should cause the recommender to rank the explanandum low. Therefore, we would like to find explanations that are both short and potent. The search space of possible explanations is too large. We thus propose three efficient search strategies besides searching randomly and exhaustively. In breadth-first search, we look for an initial explanation that we then refine. In priority search, we assign scores to explanations and explore the neighborhood of the most promising ones. In hybrid search, we start with an exhaustive search among short explanations before switching to priority search. To evaluate the search strategies, we first train a recommender, then we select users at random, request the top 20 recommendations, and pick the third item to be explained. To each search strategy, we allocate a budget, capping the number of counterfactuals tested, or equivalently, the number of recommendation requests issued. Our results show that the exhaustive search cannot return an explanation whenever a short one does not exist. This happens in 10% of the cases. Random search spends a lot of budget and returns long explanations. In contrast, our strategies identify short explanations in all cases and are highly budget conscious. Among them, hybrid search exhibits the best trade-off between speed and quality. Thank you very much for your attention.